Today we're going to be doing some practice questions on work, energy and power in A-level physics. The best way to watch this video is to actually get involved in solving the questions. So I've left links to the actual question papers with the question number in the description of this video. And in the ideal world, you guys are going to solve these questions and then you can watch this video and check your solutions. Okay, just a quick note that these are not official solutions and I'm not affiliated with the exam board, and please check out the OCR website using the links below where you'll be able to find the official questions with the official mark schemes. Okay, well, let's get started with an OCR question from 2017 from the slightly older specification. Okay, so the first part of this question is asking us to define power. Now remember, power is defined simply as the rate of work done. So we can write this. So power is the rate of work done. Part B is saying figure 1.1 shows a small electric motor used to lift an object. So we have the motor here and we have the object. The weight of the object is 30 newtons, which is pointing downwards. You have the efficiency of the motor. Then the motor lifts the object vertically at a constant speed. So it's going to be critical to the question because it's at a constant speed of 8.4 centimeters per second. I'm just going to underline centimeters because I don't want to forget to actually convert that to meters per second, which most likely you'll have to do later on. Okay, the first question is state the tension in the cable, and then we need to justify our answer. Now the tension in the cable is going to be 30 newtons because the resultant force will have to be zero if it's moving at constant speed. So this statement here, constant speed, means that the net force is equal to zero. Okay, well, let's write this down officially in our answer. So the tension of the cable is going to be 30 newtons, and let's be absolutely precise and say that this is going to be vertically upwards. And then I'm also going to say that the net force is zero because the object is moving at constant velocity. At constant velocity. Okay, part 2. Calculate the rate at which work is done in lifting the object vertically against the force of gravity. Well, the rate of work done is actually the power. So we've said this over here in the beginning, and there's an equation that we can use that power is equal to the force times the velocity. Now the force acting is just going to be 30, then the speed at which the object is moving is 8.4 centimeters. So I'm going to say 8.4 times 10 to the power of minus 2. And if we put this into a calculator, we're going to get about 2.5 joules per second or watts, so 2.5. Part 3 is asking you to calculate the input power to the electric motor. We're going to use the equation for percentage efficiency, which is given in the formula booklet, and efficiency is simply the useful energy output divided by the total energy input, and that is normally a percentage efficiency. Because we're looking for the power, and remember, power is just energy per unit time, we could really easily rewrite this equation as simply as our efficiency is going to be equal to our input power. So the output power, which is, let's call it P output, divided by the input power, like so, and this will be just our percentage efficiency times 100%. Well, So our efficiency in this question is 5%, just up here. So we can say that 5% is going to equal to our output power, which we've actually just calculated, which is the answer to the previous question. Very often in A-level questions, we often have to use the answer to the previous question. So 5% will be equal to 2.5 divided by our input power. So input, I just rearrange for our input power, which will be 2.5 divided by 5%, which is 0.05. If we divide those two numbers, we're going to get 50 watts. And the last part of this question, explain why the tension in the cable is different when the object is accelerating upwards. So at the moment, this object is moving upwards at a constant speed. So in order for it to accelerate upwards, because remember F is equal to ma, where F is the net force, this force will now have to be bigger. So if it's greater than 30 newtons, I don't know, we could have it as low as 31 or lower, but it has to be greater than 30. I don't know if it could be 40 newtons. For instance, we're going to get some acceleration. We can calculate that if we were to know the mass. But answering this in a general fashion, explain why the tension in the cable is different when the object is accelerating upwards. Well, the tension will be greater than 30 newtons as a resultant force, let's say upward force is required for acceleration. This is simply because the net force acting on an object is equal to mass times acceleration. Okay, on to the next question. Okay, next question. Once again, the link to all of these questions is in the description of this video. So figure 3.1 shows a stunt rider on a powerful motorbike at X at the top of a ramp. How exciting and potentially very dangerous. Anyway, so the total mass of a motorbike and the rider is 190 kg. The height difference between the top and the bottom of the ramp is 25 meters. The rider uses the engine to accelerate down the ramp. He leaves the end of the horizontal section with a certain speed. Okay, so the first part is just to calculate the gravitational potential energy, or the loss of GPE, between X and Y. Okay, well, remember our formula for gravitational potential energy, or the change in it in this case, will just be equal to mgh. Now the mass of the rider is 190 kg multiplied by 9.81, and our loss of height in this case is 25 meters. Plugging that into a calculator, we're going to get about 4.7 times 10 to the 4 joules. Okay, for part B, we need to calculate the kinetic energy of the rider and the motorbike at point Y. Now notice, because the rider is using the engine of the motorbike, the answer will not be 4.7 times 10 to the 4, but luckily we're given the exit speed to be 30 meters per second, and this is just a 1 marker, so I'm expecting to just use a half mv squared. Our kinetic energy will be equal to a half mv squared, so it's going to be a half times the mass, which is 190 times 30 squared, which is going to give us 8.6 times 10 to the 4 joules. So notice that this is considerably higher than the potential energy, and the rider would have had this much potential energy if they were not using the throttle, they were not using the engine, they were just coasting down. Anyways, explain why your answer to B is greater than your answer to A. Well, we've just really done that. Now let's write it down. So with these explanation questions, it's very important to be using terms, specific terms. In this case, we can use either the fact that there was work done along here, or we can say that energy was energy from the engine. There was energy added into the system from the engine between point X and Y. So let's just say that work was done by the engine of the motorbike. Okay, now the rest of this question involves calculating the the total distance traveled with a motorbike from X to Y along the ramp is 120 meters. Calculate the average accelerating force the motorbike provides along the ramp. So we can actually use the fact that work done is force times distance to do so. Now remember that work done, should we just call it W? I'm going to say that the work done W is equal to the change of energy. So work done is equivalent to the change of energy. Now the work done is simply equal to the force multiplied by the distance, and this will be equal to our change of energy, which is going to be just those two numbers taken away from one another. Now our final energy is 8.6 times 10 to the power of 4, so I'm going to say 8.6 times 10 to the power of 4. Take away the initial energy, which was 4.7 times 10 to the 4, 4.7 times 10 to the power of 4. Now a question I often get asked is what happened to the force times distance times the cosine of the angle between them. Well, if we think about it, the angle will always be 0 because the bike is always going to be accelerating along this line, essentially here, along the direction of travel. If it was at a different angle, then I'll have to do something different, but for those questions, 90% of the time, or even 99% of the time, we can just assume that the force is going along the direction of motion. So we can just use force times distance. We're also given the distance is 120, so I can even just substitute that in here. So it's going to be 120 meters. And let's just rearrange for the force. So the force will be 8.6 times 10 to the 4, take away 4.7 times 10 to the 4, and let's divide that by 120, giving us 320 newtons. And this is a really typical question of work done. Now the rest of this question involves using the Suvat equations, and I'm not going to be solving them because we have done plenty of videos on the Suvat equations. We'll do more in the future, but just for now, for this video, I would like to focus on work, energy and power. So on to the next question. Okay, next one, which is question 6 from the paper, which I've linked into the description of this video. So define work done by a force. So remember, the equation is for work done is force times distance times cosine. So it's Fx cos theta. So we can define this using words as the force multiplied by the distance traveled in the direction of the force. I included this equation just for illustration purposes. You don't actually need to do that to get full marks. I'm just going to remove this. Okay, so this is work done. Okay, part B, a crate is pushed along a rough horizontal surface at a constant speed. State what happens to the work done on the crate. Well, now because it is pushed at a constant speed on a rough horizontal surface, now the fact that it's a rough horizontal surface tells me there's a lot of friction involved into the system. So the work done will be transferred to thermal energy. So transfer to thermal energy. Okay, part C will be to define the watt. Now remember, just as an aside, every time we're defining units, we're just finding the simplest possible formula for that quantity, and then we're subbing in 1 for all of the quantities. So remember, power is energy over time, so that means that 1 watt will be equal to 1 joule per 1 second. So we can write this down as simply as 1 joule, let's say transferred or work done of 1 joule. Actually, we can just write 1 joule per 1 second, and this should give us full marks. Okay, part D, figure 6.1 shows an electric cane lifting a mechanical digger. Okay, and we have some numbers over here, like so, with a little triangle. The mass of the digger is 5,200 kg. The crane takes 1.5 minutes to lift the digger from X to Y. Calculate the rate of work done to lift the digger from X to Y. Now, in order to do so, we're going to need to find the vertical distance from here to here, because this is the distance that really matters, because gravity is acting straight down. So we're really interested in the distance traveled in that direction. So we can just use Pythagoras, and we can say, let's say if this guy here is, I don't know, x, then we can simply write down that 75 squared is going to equal x squared plus 45 squared. Now I'm just doing this on this page simply because the diagram is here, but please make sure to always write down your answers and all your work in the actual space provided in the question. Okay, well, let me just rewrite this over here, or let's just say that the vertical distance, so I'm just going to say that the vertical distance is, I'll just call that equal to x, and I'm going to say that x will be equal to the square root of 75 squared take away 45 squared, which is of course just equal to 60 meters. Now, after we've done that, we could use some formulas for energy and power, actually. So because the rate of work done is simply the power, and remember the power is equal to the rate of work done, so that's going to be W over T, or the energy over time. Now there's only one change of energy in this case, and this is gravitational potential energy divided by the time t. Now the mass is 5,200, gravitational acceleration is 9.81, the vertical height h, yeah, in this case we should have really called that h, so we'll just change that just to be absolutely consistent, so it's going to be h, and this here will also be h. Let's just change that in the diagram as well, just so that I'm absolutely clear here. Okay, so 5,200 times 9.81 times the height, which is 60, divided by the time, which is 1.5 minutes. I have to be careful, so because we need to convert that to seconds, so 1 minute and a half is 90, and if we plug that into a calculator, we're going to get 3.4 times 10 to the 4 joules per second. Okay, the last part, total input power to the motor of the crane is 170 kilowatts. Calculate the efficiency of the lifting operation. Well, our formula for efficiency, which is given in the formula booklet, is in terms of energy, and just simply says that our efficiency is going to equal our output energy, so energy output divided by the energy input times 100 normally. Now because in this case we're dealing about power, and power is just energy over time, we could rewrite exactly the same equation in terms of power. The only reason I'm writing this in terms of energy is because that's what you're given in your formula booklet. So our efficiency has exactly the same equation for power as well. So shall we just change that to P, so we can say that this is equal to our power output divided by our power input. Now our output power would simply be the rate of work done, which is 3.4 times 10 to the 4, so that's going to be 3.4 times 10 to the 4 divided by our input power, which is 170 kilowatts, so it's going to be 170 times 10 to the power of 3 times 100, and that's going to equal 20% efficiency. Okay, on to the next question. Okay, our final question for this video is question 6 from the paper. Once again, the link is in the description of this video. So part A, define work done by a force. So remember, work done is the force multiplied by the distance traveled in the direction of the force, by the distance traveled in the direction of the force. Like so. Okay, part B, figure 6.1 shows our water slide. How exciting. The top of the slide is 32 meters above the bottom of the slide. The total distance along the slide is 120 meters. A person of weight 700 newtons initially at the rest of the top slides down. His speed at the end of the slide is 15 meters per second. Calculate his kinetic energy at the end of the slide. Okay, well, we're given the speed at the end, so we can say that kinetic energy is equal to a half mv squared, so it's going to be a half times we're given the mass. We're not given the mass, actually, we're given the weight, 700 newtons, so let's just say that weight is equal to mg, which means that the mass is equal to the weight divided by the gravitational acceleration. Now the weight is 700, let's divide that by 9.81. I'm going to get a value of the mass to be 71.4 newtons, and now we can substitute that back into here, so it's going to be a half times 71.4 multiplied by 15 squared, which is about 8,000 newtons, so 8.0 times 10 to the 3 joules, so 8.0 times 10 to the power of 3 is our final answer in joules for the kinetic energy. Okay, the next one, calculate the average resistive force acting on him as he travels down the end of the slide. Okay, well, this is a very, very typical question, and the way it is solved is by always using the fact that our change of energy is equal to the work done by the resistive force. So what I'm going to say over here is that work done is equal to the change of energy. Now our work done is just force times distance, and the resistive force here is always in the direction acting towards the direction of travel. So if you're going here, they're always going to be parallel. So if your speed is this way, your resistive force will be acting in exactly the opposite way. So we don't have to worry about the cosine of the angle. Okay, well, over here we only have potential energy, and over here we only have kinetic energy. So what we can say is that force times distance will be equal to the change of energy. Now our change of energy will simply be equal to the difference between the gravitational potential energy GPE, take away the kinetic energy at the end. This is simply because right here at the top we only have GPE, and once we reach the bottom of the slide, let's say here, we have kinetic energy only. So if we take those away, we'll find our change of energy. So force times distance will be equal to our GPE, which is mgh, take away the kinetic energy, which we already have the number for actually. So force times now our distance along the slide, we're actually given this, the total distance along the slide is 120 meters. So this means that this whole line here is 120 meters. So our distance is 120, which is equal to mgh. We know that mg is 700 because the weight was 700. Now the height is 32 meters. That's going to be 32, and let's take away the kinetic energy of the bottom, which is 8.0 times 10 to the 3, so 8.0 times 10 to the 3, and our resistive force will be equal to 700 times 32, take away 8,000, like so, divided by 120. And if we plug this into a calculator, this is actually equal to 120 newtons. Okay folks, well hopefully this video was useful for you. Check out my revision video on work energy and on power, energy and work done. And thank you very much for watching, and I will see you in the next video.